Hello everyone. My name is Professor Anil Fernando from Department of Computer and Information Sciences in University of Strathclyde in Glasgow, UK. I'm a professor in vision processing and communication, and today I'm going to talk about secure image transmission with semantic communication concepts, which is going to be a new dimension of research and how information, especially the image, can be transmitted with semantic communication, and we are going to analyze whether semantic communication will provide some kind of inherent security compared to the traditional security in image transmission. To start with the presentation, I just want to give you a short introduction to my research team here in Strathclyde, and we are mainly focusing on different aspects of media transmission, and we have 20 researchers working on different aspects in media, semantic communication, image and video compression and transmission, noise modeling, multimetric for media applications, machine-to-machine and 6G media application, video coding and communications, machine learning for different applications, and future advertising. And these slides show you like how we are working in different domains. Main domain is media communication, like I explained before, and different aspects of media transmission representation system, especially with semantic communication concepts. And then some of the people are also working on energy management with machine learning, how energy can be optimized for different scenarios, insurance and finance modeling with machine learning, digital health applications, how machine learning can be and imaging technology can be significantly used in digital health applications, and final next generation networks such as compression and transmission for Internet of Video Things, quantum communications, and neuromorphic computing and IoT for media applications. With that in mind, so this is the main key people working on semantic communications, several PhD students working on different aspects of semantic communication. And to start with the presentation, let me give you a short introduction to how the basic communication system works. We have the source information. The source information can be image, video, audio, speech, or whatever it is, text, any kind of information. And then we compress this data to effectively use the channel bandwidth in during the transmission. Source encoding technique can be defined as JPEG, HEIA for image transmission, MPEG or VVC for like video compression. For audio like AAC, advanced audio coding techniques, and likewise. And then after the compression, we have a module called channel encoder. The purpose of the channel encoder is to provide some kind of redundant data to protect the source information when it is transmitted to the noisy channel. So channel coding techniques can be like the most state-of-the-art channel coding techniques is the polar codes and different other coding types like polar codes, LDPC, and so on. And then after the information is channel encoded, we have the modulator. The modulation is a very well researched domain, and a lot of applications are using digital modulation schemes such as for quadrature amplitude modulations, phase shift keying, and so on. And then after the modulation, information is pushed to the channel, noisy channel, and channel is definitely a noisy channel, which can be classified into AWGN is a hypothetical channel, then fading channel, and fading channel can also be classified into Gaussian fading and Rayleigh fading, and so on. So whatever the channel model that we use, and at the receiver side, we get a noisy signal to process, and then we have the demodulator, the inverse operation of the modulation process, and then we have the channel decoder, again inverse operation of the channel encoding process, and then after the information bits are extracted, then we have the source decoder to decompress the information, which is compressed at the transmitter side, and then finally it is feed into the display or the reproducing mode, whether we are going to use audio-based system or video-based system. Depending on this, we will have the speaker or the display to reproduce the information. So this is the whole kind of end-to-end basic communication system from starting point to the end point. So, what is semantic communication? In 1949, Shannon has proposed three problems of communication. The technical problem, which is the layer that people have been using for more than 70 odd years now for communication between 2 points, and accuracy of transference of information from sender to the receiver, like bit level transmission of the information. So that's the model that I have presented in the previous slide. Semantic problem is that we extract the information from the source, interpretation of meaning by the receiver as compared with the intended meaning of the sender. For example, if I am the transmitter and you are the receiver, I want to send an image of an elephant eating a pumpkin, for example. So that's the whole information and meaning of that information. And somehow I need to send that information to you either by sending the original information or some kind of features that you can process and then reproduce what the meaning of the information that I intended to send to you. So that is the semantic problem. Rather than sending the original bit level information, you extract the meaning and then ask the receiver to regenerate the information which is same as transmit information in the meaning level of the meaning of the information. An effectiveness problem is the success with which the meaning conveyed to the receiver leads to a desired conduct. For example, if I want to send an information to you, the water level is rising in the river, and you have to take some actions to vacate the house, for example. So, if that is the information that I want to send it to you, and I send some information, extract the features and send it to you, and you regenerate the information, and then based on that information you have to take an action. So the effectiveness problem is defined as whether the receiver is taking the action that the transmitter wants to send it to the receiver. So these are three levels of communication. Right now we have been working in the technical domain for many years, 70 odd years for day-to-day communication. And semantic problem is being emerged during the last 3, 4 years, and it is going to be play a major role in communications in years to come. And once that is saturated, problem is solved, then we can talk about the effectiveness problem. For this presentation today, I'm going to talk about the semantic problem. Whether that semantic layer will introduce some kind of additional security compared to the conventional system. So basically, those who do not know about semantic communication, I'll just briefly go through what does that mean. What does that mean? So it's conveyed by Shannon's capacity theorem, provides the condition for solving the technical problem. C is the channel capacity, the information capacity that a channel can tolerate between the two points. It's defined as B log to the power 2 base 1 plus S over N. So B is the bandwidth and C is of course the channel capacity, maximum rate of data that the channel can take between the points. And B is the bandwidth available for the data transmission. S over N is the signal to noise ratio. S is the signal power and N is the noise power. So now you can see that to increase the channel capacity, either we have to increase the bandwidth or the signal to noise ratio, which are going to be the constraints for a given communication channel. And let's concentrate on semantic communication systems briefly. So compared to the original conventional technical level communication system, here you can see that there are some additional blocks embedded to the system. You can see that here we have source encoder, channel encoder. And now if you compare this against the semantic communication, source, in between source and channel encoder, there's another block called semantic encoder. This is the place where you extract the meaning of the information from the actual information generated by the source. So once you extract the semantic features, and then we send this information and to the receiver, and this is the semantic decoder which regenerates the information at the receiving side and then use this extracted transmitted features to render the information at the receiver. So this is the semantic noise. If you fail to extract the semantic meaning fully, and there is a noise involved with that process, so that is defined as a semantic noise. For example, in my previous example, elephant and pumpkin scenario, If you extract only the information of the elephant and pumpkin is missing, the total information between the transmitter and the receiver is completely misleading. So therefore, the level of semantic rich extraction is related to the semantic noise. So better the extraction in full reduces the semantic noise and vice versa. So if you extract a lot of information, that will also consume a lot of bandwidth and so on. So there's like a fully optimization problem you need to address here. So having that in mind, so we'll go into the semantic communication system. This is the one that we are considering today, the highlighted block. An objective is modeling and improving the performance of the semantic channel such that the volume of data that needs to be transmitted in the technical channel is drastically reduced there. So therefore, the virtual capacity will be significantly reduced compared to the actual capacity in the channel. So what are we going to concentrate today is like there are two situations here. The receiver needs to have some kind of common knowledge about what the information is transmitting to from the transmitter to the receiver. So that common knowledge level of the richness of the common knowledge will improve the semantic communication framework significantly. So the definition of semantic communication, it focuses on the meaningful exchange of information, prioritizing the understanding and context behind the data transmitter that is highlighted in this first simple diagram. And then the need for the security, semantic security comes from like, since we are exchanging the common knowledge between the transmitter and the receiver. For example, we'll understand that what kind of common knowledge that we are focusing today. For example, if I have the neural network or deep learning neural network, right? Encoder and the decoder. So if you want to transmit the decoder to the receiver to regenerate the information, that transmission itself is vulnerable to the attacks. So if the decoder can be stolen by different parties, so then the information that we exchange between the transmitter and the receiver is highly vulnerable compared to the conventional system. So therefore, need for security, semantic security is quite essential, and protecting not just the data but also the meaning behind it is vital for maintaining the trust and the integrity in communication. So the aim of the presentation today is to investigate whether the semantic communication has inherent security features and to understand how the architecture of these systems contributes to the protection of transmitted data from unauthorized reconstruction. So additionally, to explore and purpose strategies, sorry, additionally to explore and propose strategies that users can adopt to enhance the security of semantic communication systems, ensuring greater resilience against the potential attacks. So in a nutshell, so what we are going to do is we are going to analyze whether the simple semantic communication system, end-to-end communication system, will add some inherent security to the communication between the two devices. So the background and motivation I explained already. So what is semantic communication? Shift from raw data transmission to meaning extraction and delivery. So potential for data efficiency and harder interpretability by unintended recipients, and motivation for this study is the lack of systematic investigation for such systems in semantic security. So what is the problem? A statement that we are going to address today is the problem statement. Traditional communications heavily depend on cryptographic layers for ensuring data security that also consume system resources. And what we are going to understand or investigate here is whether the semantic communication system, the architecture could potentially offer inherent security by abstracting data, but this possibility remains largely unexplored in the literature. So the main question is, can semantic communication systems inherently secure data transmission through design and architecture alone? So the key aspects that we are going to study here is the impact of the encoder architecture differences, role of identical initial states and architectural variations between the encoder and the decoder, effects of controlled environments with identical architectures returning data, and the initializations. So the related work, very briefly, semantic communication focus on efficiency, example, autoencoded based systems, and obfuscation of data, limited investigation into inherent security beyond encryption and traditional cryptographic methods. And encrypted semantic communication systems such as ESCS combines cryptography with semantic communication, but often assumes adversaries have similar decoder architectures. So the research gap that we have identified in this domain is the lack of studies examining security from system architecture itself, training conditions, and encoder-decoder mismatches. So the work plan is the objective is to strengthen the security in semantic communication systems, and we try to understand current framework and security gaps, conduct a literature review, and identify research gaps in secure semantic communication, which I have briefly explained before. So we try to explore autoencoder based methods for semantic communication and investigated whether there is an inherent security. So enhanced security with cryptographic techniques, simulated adversary scenarios to test resilience against data reconstruction and attacks. Basically, we have used the means data set for this kind of applications, integrated cryptographic methods to secure encoder and decoder. So we extend the semantic communication to the visual data, applied semantic communication framework to video data, higher data volumes, and so on. Incorporated cryptographic techniques while optimizing performance to balance security and efficiency. Explored alternative methods beyond AI-based frameworks to improve the security and system performance. So today I'm not going to discuss about the video, but I will demonstrate some applications based on the image transmission. So here what we are going to do is we have simulated the encoder and the decoder, transmitter and the receiver, and there's an intruder, and we call it Alice, which is in the transmitter side, and Bob is in the receiver side, and then there's an intruder called Malroy in the middle, try to replicate the information communication between the Alice and the Bob. So what we have done is we have generated the semantic encoder and decoder using an autoencoder based system, and E is the encoder and D is the decoder. There's the information channel here, and then E and D are properly trained between back to back in normal semantic communication system. And then intruder doesn't. There are several scenarios we considered here, and intruder doesn't know. In order to reproduce the data, intruder should know what is E, what is D, and also the information transmitted in the channel. So in the previous classical systems, and they don't need to know the encoder and decoder, so they all need to know is like the information about the information transmitted. The key, public key, is the only thing that is needed for the intruder. In this case, it's different because he also needs to know what is the encoder configuration and the decoder configuration to retrieve the information. So based on that, we have defined three scenarios. Scenario one, different encoder architectures, same data set, same training, but the encoder architecture is different. So we set up Alice and Melroy has different encoder architectures. So result is Melroy attacker failed to accurately reconstruct the images, indicating security through architectural differences. So this is the first scenario. The second scenario is same weights, same initial states. That means same data set plus same training. Setup we have done is like all autoencoders initialized with the same weights and carried on the same data set. And the result is Melroy still could not reconstruct the images, reinforcing that mismatch encoder pairs and enhanced security. So that's the scenario two. And scenario three is identical architectures, same data set, same training, and setup is all parties use identical encoder decoder architectures. Initialization is same and the training data set is same. So therefore, the result is Malroy successfully reconstructs up to 9 out of images in the MINTS data set, demonstrating the significant vulnerability when the encoder architecture is shared. So there are three different scenarios. In the first scenario, like encoder architectures are not known, anything is not known to the intruder. In the second scenario, the initialization process is same, and also the same data set is known for the training. And third scenario is encoder architecture is also shared. So therefore, there is a vulnerability in the scenario three. So based on that, we have done some experimentation, extensive experimentation with the MIS dataset. So there are several scenarios, like I just told you before, scenario 1, scenario 2, and scenario 3. You can see that with the reference autoencoder, you can get 98.6 accuracy, test accuracy at the receiver side. But with scenario 1, you can only get 9.6% accuracy. Scenario 2, 9.7. And scenario 3, you can see that this jumps to 80.3 percentage of accuracy, which means that so the scenario 3 is more vulnerable, very highly vulnerable compared to scenario 1 and scenario 2. So that but it's unlikely that the encoder architecture can be stolen between the transmitter and the receiver if you keep on changing the encoder architectures adaptively. So scenario 3 is unlikely, but scenario 1 and scenario 2 are most common scenarios. In that kind of scenarios, we can see that there is a inherent security embedded with the semantic communication systems, which can be highly valuable going to transmission without any additional system resources for security application. So this is some of the outputs. Outputs of Alice in each scenario and outputs of Melro in each scenario. You can see that first line. So it basically it can generate the info. It cannot generate the information at all in the first scenario. And the second scenario, there are some ambiguities again compared to the similar to the scenario 1. If you consider scenario 3, and there are some of the information can be guessed or retrieved by the intruder compared to the scenario 1 and scenario 2. So you can see that 7 is here, 7 is kind of mirrored image of this number 7 here, and 2 is again flipped and so on. So there are some possible guess that the intruder can detect with the scenario 3, and all these guesses have been considered in numerical generation of the previous result that I have showed you here. So what is the future plan? Exploring more data types, extend the study to other type of data like audio and video to evaluate the generality of the inherent security in semantic communication system. Architecture optimization, we have considered a simple architecture. Investigate different semantic communication and other inherent security applications. Explore novel architectures like deeper networks, hybrid modes to enhance both efficiency and security. And number 3, adversarial threat models. So simulate more realistic adversarial attacks. Example, man in the middle mode inversion to test the robustness of semantic communication systems with different kind of threat analysis. So those are the future plans in line with that. So the basic message you have to take on board here is the semantic communication system basically inherent some of the security features which can be effectively used for end-to-end communication systems, which will reduce the system resources significantly. With that in mind, I thank you very much for listening to this presentation, and if you have any questions, you can email me. My email address is on the first slide, and I'm happy to answer or start some kind of collaborations in these domains. Thank you very much, and goodbye from Glasgow. Thank you.